Our next speaker and the last for this afternoon session is Pavel Bleher from IUPUI, and he's going to talk about ensembles of random matrices with complex potential, phase diagrams, and topological expansion.
Okay, thank you. Do you hear me?
Yes.
Okay, first I would like to thank organizers Marco, Alberto, and Michael for inviting me to this conference. It's very exciting and to celebrate John Harnett, and because we're friends with John for more than 25 years, and he was very active and very, I would say, influential participants of our first meetings on random matrices. It was Mount Holyoke meeting in 1996, and then a big program at MSRI. And I remember very well his fantastic talks about this integrable relations in for random matrices, and for me it was extremely interesting and extremely important. Right, then this was continued. Let me see. Right. So in 2008, 2009, John kindly invited me to join him in the organizing committee of one-year program on probabilistic methods in mathematical physics at CRM, and this was spent quite a lot of time there at CRM, giving some lectures, and also then John published my lectures in the volume he organized, and also I was working with my graduate student Carl Lichty at that time on random matrices and applications to six-vertex model, and we wrote a book which is published in a CRM a lecture series. Okay, so and for me, always, I mean, interaction with John was very enjoyable and very interesting and very useful. So and I'm really very glad to be here. Okay, so I will talk about about random matrices of complex potentials and topological expansions, right? And this is my ongoing project with several people listed here: Ahmad Barhoumi, Mark Bertola, Alfredo Diania, Uzbek Gahlu, Ken McLaughlin, Alex Tobis, and Maxim Yatselev. So different parts of this work were done with these people. Right, and so let me begin with a brief review of the topological expansion in the in unitary ensembles of random matrices. It's very classical and very interesting topic. So let us begin with a real polynomial, v of x, sum tj fj, right, and degree of the polynomial is even, and the leading coefficient is positive. Then corresponding unitary ensemble of random matrices is the probability distribution with weight function, like in statistical mechanics, E minus energy, which is in this case minus n times trace v of m. V is this polynomial, m is our matrix, and Hermitian matrix, right? And then dm, and then we have to normalize by partition function 0 of statistical physics, right? And this gives us probability measure on the space of Hermitian matrices. And what we're interested in, the main question is thermodynamic limit when then goes to infinity. What can we say about asymptotics of z and about correlation functions and right, and phase transitions, phase diagrams, and parameters, and so on. Right. So now let me, as an example, consider quartic polynomial. Right. x squared over 2 plus u x to the fourth, and u is coefficient at the fourth power, T4, and it is positive. Right, the partition function of the quartic ensemble is just this integral over the space of matrices, right, of this weight function. Now, when u equals 0, then we have just x squared over 2, it's quadratic, it's a Gaussian unitary ensemble, and then partition function is very easy to calculate. It's given by this formula. Let's consider normalized partition function. It is the quotient of 0 n of u divided by 0 of 0. Right, and then to get topological expansion, let's make the change of variables very natural. M prime equal m times square root of n. Right, then denoting m prime back by m, we obtain that the normalized partition function is the same integral, but n now in denominator. Yeah, right. Okay, so now we can view it as the following. So on the top, we have integral with this extra term in the weight, quartic term. On the bottom, we just have Gaussian ensemble. And so it's mathematical expectation of this quartic term, exponent of the quartic term. Right. And so now what we do to get the topological expansion, we expand this, this exponent in the mathematical expectation into Taylor series. And we calculate term by term the mathematical expectations. So, right, so in the Gaussian ensemble, the entries are independent, and the correlation functions, it is just Gaussian correlation function, so it's 2-point correlation function, is very simple. So it reflects that the matrix is Hermitian, right, and so it's written here. So now let us evaluate the first term here, the terms here, I mean consecutive terms in this sum. And so EP is just mathematical expectation with respect to Gaussian ensemble of trace of m to the fourth to power p. Right, and so let us start with E1. Then there's this mathematical expectation. Now we can use the Wick theorem, which tells us that to calculate the fourth moment, we have to consider partitions of the 4 points into pairs. Right, and in this way we'll get the explicit formula, which is called Wick theorem. And because we know, right, these correlators, P correlators, it's immediately we'll get these formulas. And now we have summation over IJKL, and all the terms are right. So everything is partitioned into 2 types of term related to IK, KL, and this product, and sums over just IK and KL give us terms in Q, but this term give us N. And so in the end of the day, we'll get that E1, this mathematical expectation is 2NQ plus N. Right. And so these terms can be represented by the Feynman diagrams with 1 vertex. The first and third diagrams are planar of the genus G equal 0, the diagram, and the second one is toroidal of genus G equal 1. Here, right, they are very simple. So this is this diagram, Feynman diagram, can be plotted on the sphere on the plane, but this one is plotted on the torus. Right. And so what we have that E1, as I said, so it is 2NQ plus N, and the N cubed terms correspond to 2 Feynman diagrams or graphs on the plane or sphere. And the power 3 is the number of faces in this graph, this power. The n term corresponds to the Feynman diagram on the torus, and the number of faces of this graph on the torus is 1. And so we get that E1 can be written as sum over pi's graphs n to power f of pi, where f of pi is just the number of faces. So this is for E1. This can be extended to E2, E3, and so on. What about E2? When we consider E2, it is trace m to the fourth of square, and then mathematical expectation. If we multiply out completely, this trace will get these 8 terms. Right, and now again we use weak theorem, and this gives us sum over all partitions of partitions pi of this set of points, of these 8 points, into pairs. Right, and so now when we consider partitions, we'll have 2 types of partitions. One type is the disconnected graph, and second part is connected graphs. Right, and so disconnected graph just gives us E1 square, where E1 was the first term, and the second part is called connected part of Feynman diagrams. Right, and so these are examples of regular connected Feynman diagrams of degree 4 with 2 vertices. It is what corresponds to E2. Right, and these are from E to C because we consider connected graphs. So this, the first graph is reproduced on the plane, on the sphere, and so it is genus 0 surface, and this graph is reproduced on the torus. This corresponds to the genus 1. Right, and so what we have that here, the connected part of E2 is sum over all Feynman diagrams n to power f of pi, where f of pi is the number of faces of this diagram. Right, and this can be easily extended to any p, and what we have that the connected part of EP is represented by sum over all graphs n to power f of pi, where pi are connected diagrams with p vertices. Right. Okay. So now we're interested in the asymptotics of partition function, and it is very convenient to introduce normalized free energy as a logarithm of this normalized partition function divided by the number of degrees of freedom. In our case, we have n square elements, and so we have to divide by n square. Right, and now we can apply the second weak theorem, and it tells us that the free energy, so when we take logarithm, we had some expression for Zn of u divided by Zn of 0, then we take logarithm, it should be more complicated, but in fact it's simpler. And second weak theorem tells us that Fn of u is similar sum as for Zn of u, but only connected diagrams survive. Right, and so what we get that free energy is this sum for p equals 0 to infinity. P is the number of vertices. Right, and then we have some minus u to power p. Right, it comes from here. Then, well, p factorial, so already from the exponent. But then we have this sum over all Feynman diagrams n to power f of pi minus p, where f of pi, remember, it is the number of faces. Right, now we can apply the Euler formula, and this gives us, that f of p what's written here is just nothing else but 2 minus 2g, where g is the genus of the surface. And we get this very nice formula for the free energy in terms of sum over all Feynman diagrams connected. Right. And so this is the starting formula for the topological expansion, how to get it. Now we interchange the order of summation here, right? And so first we make summation over partitions and then over P, right? And so what we get is the second term is just number of connected regular Feynman diagrams of degree 4 with P vertices on a closed oriented Riemannian surface of genus G. So this is this guy, right? And right, and this is called topological expansion because it is expansion of Riemannian surfaces of genus 0, 1, and so on. So why it's so interesting? Because if we look at the coefficients of 1 over n square expansion, these are generating function for the numbers A, G of P, which is the number of connected regular Feynman diagrams of degree 4 with P vertices. Right, but if P is large, that Feynman diagram of degree 4 can be viewed as an approximation of a metric on the Riemannian surface. And in the limit, when P goes to infinity, this gives some integral over metrics, and so it is gives connection to quantum gravity. That's why, right, this topological expansion is right is very interesting and important. So these coefficients of topological expansion are generating function for the number of connected regular Feynman diagrams, right? And right, and so the 1 over n square expansion of the free energy is called topological expansion. So far, my calculations were formal when I interchanged the order of summation. And so mathematically, the questions are to prove this rigorously, this existence of topological expansion, and also to calculate these coefficients and the numbers A, G of P, which are the number of connected graphs of degree 4 with P vertices on the closed oriented surface of genus G. Right. So now there are many works on topological expansion, and both in physics and mathematics. Here I listed some of them. Right, and it goes back to classical works of Hooft, Brizan et Saxon, Preis-Zuber, Brizan et Saxon, Zuber, and so on. Right, and mathematical literature is also now rather big. Right, and some contributions are listed here. Okay. So now the Riemann-Hilbert approach to an evaluation of topological expansion gives two things. First, it gives rigorous proofs of the topological expansions, and also it gives some efficient ways to calculate the coefficients of topological expansion. So to do this, we say for the quartic model, which I will discuss mostly, we consider the partition function of the ensemble of eigenvalues. Right, and the free energy can be expressed as logarithm of reduced quotient of partition functions of the ensemble of eigenvalues. This is usual formula in the theory of random matrices. Right. So, and important, the first step in the Riemann-Hilbert approach is to reduce, to express partition function of eigenvalues in terms of orthogonal polynomials. Right. So now we can see the orthogonal polynomials with this weight. So it is monic orthogonal polynomials, and the weight is E minus n just V of x. In our case, it is what's written here, quartic polynomial. Right. And this polynomial satisfies the free-term recurrence relation with, right, which written here again, it's very well known, and Rn is the quotient of normalizing constants. And the recurrence coefficients also satisfy what is called the string equation, right? And it is a nonlinear equation for the recurrence coefficients. It's written here, right? So now, now what we're interested in the asymptotics of the partition function. Partition function is a product of normalizing constant, but this formula is not very convenient because we are interested in large n limit of Zn and asymptotic expansion with respect to n capital. But here we have a product, and this product involves small n. Small n equals 0, 1, 2, and so on. And we don't have asymptotic expansions for these coefficients. And so we have to use something different. And something different is the following. So first we prove the uniform topological expansion of the recurrence coefficients. And recurrence coefficients depends, of course, on the parameter u and on parameter n, but for me, it would be more convenient to consider parameter, right, eta as n small over n capital. N small is the degree of the polynomial, and n capital is parameter in the weight. Right, and the first step is to derive asymptotic topological, I would say topological expansion for the recurrence coefficients. Right. And with this Riemann-Hilbert approach, we can prove the existence of this expansion. And also we can prove that the coefficients in this 1 over n squared expansion are analytic functions of eta and u. And we're mostly interested in this case, at the moment, at u equals 0 and at eta equals. Right, it will be clear very soon why. Right, and so the claim is that these coefficients are analytic functions of eta and u. Right, at this point. So now we can calculate these coefficients very efficiently if we use the string equations. Namely, we take asymptotic expansion of these coefficients and we substitute and consider different powers of 1 over n squared. And this gives us some recursion equations which we can use to calculate the coefficients. So, for instance, the leading coefficients are 0. This is coefficient here, right? So it is just the limit. I0 is just the limit of In. Right. Is solution of this Pareto equation. Right. And so we get immediately the solution I0. Now, if we consider higher order coefficients, then if we consider the term 1 over n to power 2g, in the asymptotic expansion of the recurrence coefficient, then we'll get this equation, which gives us, which is nothing else but a recursive formula for RG. RG is expressed in terms of previous coefficients and their derivatives of respect to parameter eta. Right, and this way we can find R1, R2, and so on. So now, next step, we go from topological expansion of recurrence coefficient to topological expansion of free energy. Right, and the key point here is the following deformation equation, which is one of these features of the random matrix model, which is related to integrable structure of this ensemble of random matrices. Right, and so what we have is this deformation equation, which gives us derivative of partition function entirely in terms of the recurrence coefficients. And what's very important here, that here we have recurrence coefficients only for large indices, n and -1 and n plus 1. And we already know asymptotic expansion of these coefficients. And so this gives us topological expansion first for Fn prime and then for Fn. This is the idea. Right, and so as a result, we give a rigorous proof, a complete proof of existence of topological expansion for the free energy. And also we get very efficient way to calculate these terms, which I remind you is related to generating function for counting graphs on the Riemannian surfaces of G. Right, and this relation is given in the following way. So we have asymptotic expansion of in powers 1 over n square of free energy, and coefficients are generating function for the number of Feynman diagrams, or just graphs, regular graphs with p vertices with 4 variant of degree 4. Right, and so this is extremely simple and very useful formula to calculate these numbers. Right. So this was done by BC, Satsitson, and Bleher long ago for 0, 1, and 2. These are a number of on the sphere, on the torus, and Riemann surface of genus 2. These are explicit formulas. And so what we did, we just proved this formula rigorously. Right, and in fact, we calculated also the next term, and in principle, you can continue, but the formulas becomes rather complicated. And what we would like to do is to find large p asymptotics of these numbers. Because when we go to quantum gravity, we need p is taken to infinity, because p is the parameter of approximation of the metric. Right, and so this asymptotics can be calculated. We calculate this, and it's given by the following formula. So it's some constant which depends on G, on the genus. Right, and as p goes to infinity, this is the number of vertices. We have this explicit asymptotics. We can calculate also subleading terms, but mostly we're interested in the leading term. Right, and let's now look at constant. It depends on the genus, and it can be calculated as follows. So it is expressed in terms of some different constant, c, which we call c script to g, and the constant c to g can be found recursively by this formula. Right, it is quadratic recursion. C to G in terms of previous C's, and if we look at this formula, we can notice that the constants CG, right, or rather C2G, already are known. They appears in the Berthoud truncated or three-truncated solutions of the Penlever-1 equations. Namely, if we consider the Penlever-1 equation, which is written here, and make a scaling of very simple scaling of the solution, then x goes to infinity. We have this. In fact, it's asymptotic expansion in powers of x, right? And if you look at the recurrence equations for yg, you can notice that they're exactly the same as the recurrence equations for C2G. Right. And instead of C2G, I put here CG. I'm sorry. Right. And so somehow miraculously, this recurrence coefficients, right? This coefficient C2G are related to Penlever-1. And so, and to understand this better, we consider the right. We consider the following thing. So I remind you that we have from the very beginning, we have Taylor series. Fg of u is Taylor series with coefficients Ag of p, normalized by 4 to the power p and p factorial. Right. And so if we're interested in large p, then what should we do? We have to consider this function on the complex plane and find the closest, extend this to analytic function. It's an analytic function in the neighborhood of 0, but to extend it to the complex plane and find the closest singular point and to calculate the behavior at the singular points. Right. And right, and now this is the motivation that to consider ensemble of random matrices for complex values of u. Right, for u on the whole complex plane. But now the integral is well defined when real part of u is greater than 0, but it diverges when real part of u is less than 0. And there are different ways to, then we need to regularize this integral. Right, and there are different ways to do it. One of them is rotate the contour to keep the integral convergence. And this was done by Marco Bertola, right, in his works with Sasha Toblis and others. Right, but another way is to make a change of variables. From z we go to zeta, and we introduce new parameter sigma instead of u. Right, and then we consider this quartic model with after this change of variables. And the advantage here now that the coefficients at z to the 4th is 1 now. And so the integral is convergence everywhere, and it gives us analytic function of sigma. Then if you would like to go back to u, we just use this this covering, right, of u plane. Right, and you can get depiction on the u plane. Right, and the partitions functions are also very easily connected. And so we're interested in this partition function of this random matrix model of this polynomial. So now this idea goes back to physicist Francois David. And right, and what we're doing we are following his intuition and his non-rigorous calculations. First of all, to make everything rigorous, and then to calculate various things. Right, and in what follows, I will present my results with Ken McLaughlin and Rosberg Garthon. Okay, so let me begin with the phase diagram. So now we are on the sigma plane. This is the phase space of our model. Now it is a sigma plane, complex sigma plane. And this is the phase diagram, which was numerically calculated by François David. Right, and we have these three regions, I would say pure phases, one cut region, two cut region, and three cut regimes. Right. So now these are the red dots are critical points, and I will explain in what sense. But this critical point, which is sigma equal -2, corresponds to double scaling limit of Penlever 2. And this one corresponds to critical point of Penlever 1. So now, if we go back to U variables, then this point will be the closest to the origin, and it is described in terms of Penlever 1, the singularity of free energy at this point. And this explains why in the asymptotics of Taylor coefficients we have Penlever functions. Right. So the explanation is that because double scaling limit, right, at this point is described in terms of Penlever 1. Okay. So right. So now to apply the classical Riemann-Hilbert approach works on the real polynomials, and so basically it works on the real line in the sigma plane, and so we have to extend it, try to extend analysis of orthogonal polynomials to complex weights, and right, and this is and here we use very recently works, all right, on the equilibrium measures on the complex plane, which are called max-mean equilibrium measures, right? And we use here concretely the work of Arno Kairats and Guilherme Silva. And let me just briefly describe the result. So we consider the contour gamma on the complex plane. It is basically the contours of integration for orthogonal polynomials. Now it can be not only a real line, but a contour on the complex plane. Right, and we consider some class of contours. It's they're called admissible. Right, and it goes from -infinity to +infinity on the real line. And it is a finite union of analytic arcs. Right. So this is the class of contours. And now we consider the space of probability measures on this contour, and we introduce the energy functional. It is the basic fundamental step in the Riemann-Hilbert approach and also in physical steepest descent method, right? And the energy is given by P energy with log its Coulomb energy, and then we have external source or external field V, And here we take a real part of V and we integrate with respect to nu. This is the appropriate energy functional. And by very general results of the potential theory, there exists a minimizer, well, this measure, which are called nu gamma, of this functional. So that if I consider minimum of all probability measures of this functional, then it is attained in this minimizer. This minimizer exists and unique. This is a very general result. But now we have this minimizer can be described in terms of Euler-Lagrange variational condition, and this is very useful. So the support of the minimizers is some compact set. In fact, it is a set of intervals, union of intervals, and it is determined by this, uniquely determined by Euler-Lagrange variational conditions. And on the support of this this measure, we have this Lagrange multiplier L, right? And this is a variational condition, right? But outside of the support, we have inequality. It is very similar to the Riemann-Hilbert problem, to the Riemann-Hilbert situation on the real line. Right. So what is changed here? We take real part, and the contour can be contoured in the complex plane. Right. And U is just Lagrange potential. So these are Euler-Lagrange variational conditions. Right. And then to get the equilibrium measure, we have to maximize the energy of the equilibrium measure over the set of admissible contours. And what Kailars and Silva proved that the maximizing contour exists. Second, the equilibrium measure is supported by a set J, which is a finite union of analytic arcs, which are called cuts. Because I have cuts of the resolvent to right. And so these are intervals from AK to BK. So we assume that on gamma 0, we have some parameterization from minus infinity to infinity. And so this is from AK to BK. And so the support is just finite union of intervals on gamma, or on gamma 0 in this case. And fundamental fact that these arcs are critical trajectories of some quadratic differential. Quadratic differential minus R of Z d z square, where R of Z is a polynomial. Okay. This is right. I will return to this to critical trajectories just on the next slide, explaining this. Right. And second thing is that this support of the equilibrium measure is unique. The contour itself, gamma 0, is not unique because we can deform it outside of the support of equilibrium measure, but the set J is unique. Right. So the fact that these arcs are critical trajectories of the quadratic differential means that at the endpoints, R is equal to 0. So the endpoints are zeros of the function R. And inside of the support, minus R d z square is strictly positive. Right. And right, and the very essential part of the theorem of Kailars and Silva is some I would say, explicit formula for the polynomial R of Z. It is, yeah, right. And so it is the following, that R of Z is equal minus omega of Z, where omega of Z is the resolvent of this equilibrium measure, plus V prime of Z over 2 squared. And it is extremely powerful and important equation. It doesn't give explicit formula for R, but because because omega itself is represented right as an unknown integral, but still it is extremely powerful formula. Right, now the equilibrium measure nu zero is absolutely continuous with respect to arc length, and its density is given in terms of square root of R, limiting value from plus side in this case. Right. And plus side means if we move from minus infinity to infinity, it is on the left-hand side. Okay. Right. So now, as in the theory of equilibrium measures on the real line, we distinguish between regular and singular equilibrium measures. And regular means that all these arcs are disjoint and the endpoints are simple zeros. And outside of the support, we have strict inequalities in the Euler-Lagrange condition. Okay, yeah. Here it is greater or equal, but if it's regular, then it should be strict inequalities. If it is not, then it's called singular. Right. So now let us consider this function R of Z for the quartic case. Right, V of zeta sigma is quartic polynomial. Right, and we'll get R of Z is minus resolvent plus derivative of this, which is Z cubed plus sigma of Z divided by 2 squared. Now this is this gives a lot of information about R of Z. In many cases, it's right, completely determines R of Z, but not always. Right, and the key point is that the resolvent decays at infinity as 1 over Z. And so when we consider behavior at infinity, here we have explicit asymptotics, polynomial asymptotics as Z goes to infinity, and this gives us right, but this gives R of Z. Right. But this gives us leading term of R of Z, I would say. Right. So now, in the case of quartic polynomial, we have additional information about R of Z because V of Z is even polynomial. And so this implies that the equilibrium measure is even, and the resolvent is odd, and the polynomial R is even. Right. And so now, right, what we have, of course, immediately, that R of Z is a polynomial of the 6th degree, if we consider polynomial infinity. Right, and so there can be 3 cases: 1 cut case, 2 cut case, and 3 cut case. It depends on the number of intervals, but not more than 3. Right. So if it is 1 cut case, then R of Z has the following structure. We have simple zeros at the end of the interval, and in this case, because of the symmetry, the interval, the support of the equilibrium measure is from the endpoints are minus B1 and plus B1. Right, and Z0, minus Z0 and plus Z0 are double zeros of our Z. Right, and they're just not endpoints. So now, if we equate our formula for R of Z with this expression, so the leading terms are Z to the 4th, Z to the 6th plus 2 sigma, Z to the 4th, then quadratic term, and then constant term, M2 is the second moment of equilibrium measure. We don't know this, but still we get two equations for B1 and for Z0, these coefficients, and we can solve them. And this gives us the endpoints and double zeros of equilibrium measure. So this is an example, numerical example for sigma equal 1 plus I. This is a one-cut equilibrium measure. So the support of equilibrium measure from minus B1 to B1, it's just along this curve. And we have two double zeros of the function R, Z0 and minus Z0. Okay. Hello?
Yes.
Okay.
Yeah. Go ahead.
Right. Okay. So in the when we have two-cut case, then we have two intervals, R1, B1, and minus B1, R1. Right. And then the double zero is just at 0 because of the symmetry. And in this case, we get equations on the endpoints, and right, we get just two equations, simple system of two equations. We can solve it for A2 square and B2 square. Okay, right, and this is numerical example of two-cut case. This is for sigma equal minus 3 plus I. So we have two intervals of the support, two cuts, minus B2, minus A1, A2, B2, right, and double zero at 0. Okay, right, and so in these shaded regions, we have this Euler-Lagrange inequality strict. This is extremely important for the equilibrium measure. Okay. Finally, in the free-cut regime, the equilibrium measure consists. The support of the equilibrium measure consists of the three intervals, and we have algebraic endpoint equations that only two equations, and then in addition we have two real equations which are transcendental. They are given in terms of integrals. And they follow from the Euler-Lagrange equations because, right, the measure is basically positive, right? And so we have these two additional equations, but they're not algebraic. And this has very important implications on the solutions for endpoints. Right. So this example of the support of the equilibrium measure in the free-cut case, and for as an example, sigma equal minus 3 plus 2i, right? So these are two symmetric intervals, and one is just around the 0, minus A3, right? And now we have the following description of analyticity of the equilibrium measure. In one-cut and two-cut regimes or regions, the equilibrium measure depends analytically on the parameter sigma. Basically, it means the endpoints depend analytically. And it can be understood very easily because, say, in two-cut case, we have explicit relation. We have basically algebraic system with very simple solution, and this gives us analytic formulas. And similarly in one-cut case. But in the three-cut case, we have these two real equations, and as a result, we have the following statement that the equilibrium measure depends analytically on the real part of sigma and the imaginary part of sigma, but not on sigma, so that the Cauchy-Riemann equations fail. They fail for the endpoints, basically. Right. And from the point of view of statistical physics, these are the free-cut region is singular. It's not. It consists of critical points because, by definition, in the pure phases we have analytic dependence, say, of free energy on sigma. But here we don't have, and so in this sense, and it was already mentioned, noticed by Francois David. He said that something that the measure does not exist in some sense. Right. So now, returning to phase diagram and phase transitions, I can present the following results. Some time ago, with Bertrand and Nard, we proved that the critical point, sigma equal -2, the free energy exhibits a free order phase transition on the real line. This means that the free energy and the first two derivatives are continuous, but the third derivative is a jump. At this point, the free energy is a function of sigma, real sigma. So now with Alexander Ritz, we proved that the critical point sigma equal -2, the double scaling limit is described in terms of Penlever-2 functions. This this classical solution of Penlever-2. And Morris Dietz and Arno Kallas, they proved that the critical point 12I is in fact at the critical point, the double scaling limit is P1. It's described in terms of P1. So now, in my remaining time, I want to present some explicit expressions for the critical curves. So let me, so we describe behavior, critical behavior, double scaling limit behavior at this point, but now I would like to describe these critical curves. So one description is sort of transcendental. We have that corresponds to the case when, say, in one-cut regime goes to three-cut regime. That means that these double zeros, they come to they either birth of a cut or right, or the cut is divided in two parts, split of a cut, right? But these are transcendental, very unexplicit description. What we have is very nice and very explicit description in terms of quadratic differentials, and this is what I want to describe now. So to do this, let us make substitution sigma equal -3 for beta plus 4 for beta, and let us consider the preimages of critical curves on the beta place, on beta plane. And then the claim is that these critical curves are mapped on the critical trajectories of this quadratic differential. So this quadratic differential has 4 zeros. Okay, some of them are multiple zeros, and this pole at infinity. Right, but this gives because the theory of quadratic differentials is very well developed, this gives, I mean, the existence of the critical curves and many properties of them. Right. So now let me summarize our main results. So the critical curves are determined by quadratic differentials. I described only from 1 to 3, but there is even a simple description from 2 to 3 critical curves. Right. Now the associated orthogonal polynomials admits 1 over n square expansion in one cut region, and free energy also admits one topological 1 over n square expansion in the following in the one cut region. Now, this still an open question is what can we say about topological expansions in 2-cut and 3-cut regions? And in 3-cut regions, something weird happens. I mean that orthogonal polynomials do not exist on some lattice of points, and in this sense, we cannot expect this usual formulation of the topological one-way expansion. I believe something can be done, but it is similar to this KM theory when we have resonances. Right. So now cubic case is also very interesting in terms of topological expansion, because it gives asymptotics of Feynman graphs of degree 3 on Riemannian surfaces, or equivalently number of triangulations. In this case, we need regularization from the very beginning, because for any u, even u positive, the integral is divergent, but it can be done. Right, the phase diagram of this is described in David, and we rigorously investigated it together with Barhumi, Diani, and Yatsi. Okay, that's it. Thank you.
Yeah, thank you, Pavel. Let me ask if there are questions here in the audience or at home. I have a question. Alberto, just a second.
Can you hear me?
Yes, Alberto. Very well.
Going back to the very beginning, and I don't know anything about these matrix models, but you use this Wick formula, which gives you a way, in the simplest case, you have a bunch of independent mean zero Gaussian random variables.
Right, absolutely.
And take the product, x1, x2, xn, and there is a way of computing the expected value. This is now that, and I realize now you're doing perturbations of that and so on, but stick to the basic Gaussian case. If you have, again, a collection of independent, I'm sorry, not independent, I should say correlated but jointly Gaussian random variables with means that don't need to be zero, there are formulas in terms of summing over contributions from graphs. If you have, instead of x1, you put a Hermite polynomial of degree n1 of x1 times another Hermite polynomial of degree n2 of x2, the product of these guys.
Yes.
Do they play any role here? I mean, one can write formulas in the Gaussian case. And now you are counting, I presume, graphs that have different degrees. Now the degrees are going to be n1, n2, n3 at each one of these vertices. And presumably there are perturbations of that too.
Right. Okay, the answer is that probably it describes some different combinatorial setting, but but I'm not sure what kind of combinatorial problem we will get. So here we're counting the number of graphs. If it is Hermite polynomials, then I don't know.
I mean, in some other language, instead of Hermite polynomials, these people call the things Vic. I mean, I forget the notation. You have a field phi to the n, and you put two dots on each side, whatever, the time order version of that or the Vic polynomial.
Yeah, so you have some moments related to the Hermite polynomials.
Mhm.
I understand this, but I'm not sure how you can, what kind of combinatorial problem you can solve with this. This I don't know.
Okay. I'll try to connect with you by email. Okay.
Of course, of course.
Thank you.
Sure, you're welcome.
Yes. Are there other questions? I actually have a question myself. So you got this description of the phase transition curves in terms of a quadratic differential, right?
Right.
Now, right. So the question I have is this a happy accident, or it should happen for other polynomial?
This is my hope.
And so in general,
for cubic, we know for cubic the same thing for cubic ensemble. Then it's even simpler.
now suppose that you have a polynomial potential where you have additional parameters, not just sigma.
Yeah,
You have
right.
two, right. So is it possible to get some kind of now the phase transition is a surface?
Yes, exactly. For instance, if you consider quartic plus cubic.
Yeah. Okay.
But then I don't know the answer.
Okay.
It is very, very good question, but we're planning to look at this together with you, by the way.
So I think that the reason the underlying reason why you get the transition here is
Yes.
the phase transition curves by quadratic differential is because on those transition curves, you have effectively just one cut. Even if those are the separating curves between genus 2 and 3 curves, right?
Right, after this mapping.
Yeah.
Right.
In general, I'm not so sure. Okay, so.
Yeah. Right. But what I want to say is that on the beta plane, we have these critical trajectories, but some of them are what's called to fake.
Fake, okay, yes.
Yeah. They do not correspond to the real critical trajectories, critical curves on the sigma plane.
Yeah. Okay, all right. Okay, thanks, Pavel.
Of course.
Any other questions? Doesn't look like, so we can thank the speaker.
Okay, thank you so much.
Thank you, Pavel.
Thank you.